Mm, Good afternoon, dear course participants. Uh, in the Geospatial Modeling for Watershed Management course series, today I am delivering third lectures, which is Geospatial Modeling for Soil Erosion Assessment in Watershed. Here in this lecture, I will cover how we are using G- remote sensing derived input parameter and integrating in GIS to prepare a spatially distributed soil erosion map. In that, uh, I will discuss some of the models, erosion models, which are primarily being used in soil erosion assessment in watershed, and that you can utilize for, because that soil erosion assessment map used as a tool or as a input for land use planning for in watershed for soil and water conservation measures. So as tomorrow we will go for the soil and water conservation measures, but before that we want to know how to estimate soil erosion on spatial basis. If you see soil erosion processes, then soil erosion we can define it is a process of the detachment of the particle, soil particle, its transport from its original place to other places or go for loss into the stream, and deposition on the way in the land surface. So detachment, transport and deposition by the erosive forces of rainfall and surface flow of water. So rain particles when falls on the ground, they detach the soil particle, and these soil particles becomes loose material, and they get transported through runoff, which is generated over the land surface, because part of the rainfall get infiltrated into soils and remaining parts moves on the surface. We call it as a surface runoff flow of water. If we see the what are the important processes in erosion, so first process is splash erosion, where a part when a rain hits the particle soil surface, then particles get detached. Second is the sheet erosion, where the thin layer of the soil from the surface removed, and it because of that we call it is sheet erosion. Rill erosion, when the runoff water flow in depressional area as a concentrated flow of runoff water. So when concentration of runoff water has increased because of depression on the land surface, then the velocity of the runoff water also increases and amount of water is more. Therefore, erosive action will be high. So more sheet erosion will occur in that case, and the depressional area becomes wide. And if they are narrow one and not so deep, then it is rill erosion. When it becomes a very wide and deeper, then we call it is gully erosion. And also one form is there, tunnel erosion or piping erosion, which is not very much common. It is in some of the problematic soils where in subsurface there is a gypsum layer or some holes are created by the animals. Because of that, tunnel erosions take place. So primarily you can say splash, sheet, rill and gully erosion are there. If you see, if sloping land is there, then primarily when raindrops falls, then it flow from the top of the hills or top of the hill slope, then there you will get mainly the sheet erosion. When it goes and it concentrated into the depressional area, then it forms the rill erosion. And many of the rills, when they get water get accumulated and large amount of water when moves, then it generate or it create gully erosion. So this is the soil erosion is a step-to-step process. Means first is to start with splash, then sheet erosion, then rill erosion, and gully erosion. So yeah, if you see how we can classify which are the rill and which are the gully, then you can say that if width is less than 10 centimeter, then it is called small incision, and rills are having 10 to 30 centimeter wide, and depth is less than 20 centimeter. Gullies can be divided into small gullies and large gullies. Small gullies 30 to 70 centimeter wide, or up to 1 meter you can say, and depth is 20 to 70 meter, or up to 1 meter of depth. Large gullies are more than 1 meter deep and more than 1 meter or more than 70 centimeter wide. So these are called gullies, and also some of times it is like a stream, or streams are basically primary gullies. If you see this process in the pictorial forms, this is splash erosion. When rain particles are falling on that, detach the soil particles becomes loose. This is the sheet erosion. You see the part of the area, thin layer of the soil is removed, so sheet erosion. And when this sheet erosion and then run of water concentrated and moves in the depressional area, then it forms the rill. It is rill erosion. So rill erosion is, you can say, if you plow the land, then it get disappeared also. So after rains, many times we are not able to visualize the rill erosion and sheet erosion. But gully erosion is the advanced form of the rill erosion, and where a large amount of soil is removed from the surface and subsurface is exposed in that case. Subsurface soils get exposed and wider, and this is mainly the dissected lands, you can say. If you see in the field, this is the top soils get removed, so sheet erosion. Here you see when rain falls on that surface, then runoff water moves on that, it removes the top soil layer, and that's why you are seeing the runoff water as because of soil or sediments, you are getting such color. And along the field boundaries, when the slopes are there, you will find that is the landslip or landslide. Landslide comes under the geologic category, but here you can say the landslips in the agriculture field. This is maize crop and agriculture field, that side slopes are getting removed. And you see this is a tree, but its adjoining soil has been removed by the landslip. So how we can see on the satellite data, how it appears on the satellite data. If you see, here I have shown one area, that is the Google image, where you are getting natural color composite instead of false color composite. And you see here that is the ISRO Bhuvan portal. If you go, then you can see that is the 5.8 meter spatial resolution satellite data, means high spatial resolution data. And you can see here this is the gully. If gully are there, then certainly the adjoining area will be affected by your sheet erosion. So sheet erosion, if you are getting the sheet erosion, then you can say the moderate erosion. Sheet erosion is your moderate erosion, and if you are getting gullies, then it is severe erosion. So this is the severely eroded lands, but adjoining land is moderate erosion. And if you go to the top of here, this area also will get sheet erosion. So you can see by visual interpretation of satellite data that if you are taking high spatial resolution satellite data, then gullies can be very easily mapped, and gully and then adjoining area as a sheet erosion area, that can also be assumed. Because when you are interpreting the satellite data, you should take into account the factors of what factors are affecting the soil erosion. So topography, vegetation cover, and soil types are the important. So topography and vegetation, two things has to be taken into account. If vegetation, even the forest area, you see this is the forest area, green color it is shown, dark green, but you are seeing this linear feature. This linear feature is gullies. This linear feature, it is appearing a stream, it is a stream and also serves as a gullies. It is formed with gully formation. So even in the forest area you are getting the gullies, and then adjoining area will be affected by moderate erosion. So you can interpret it once you visit the area, then you can make out these informations and you can interpret satellite data by visual interpretation. You see here that is the this false color composite of satellite data, false color composite satellite data, and you can see if the sheet erosion is taking place, then top layer is removed, then it becomes rich in sand content and poor in organic matter content. That's why you are getting high reflectance and it is appearing as a whitish stone. But here you see lot of dissections you are getting. This is the very severely eroded lands, and you can say these are the gully. So gully erosion, sheet erosion, and in between that land certainly will be moderate erosion. So here you can classify as a moderate erosion. Here you can see another pictures. You see this one, you are getting the linear irregular features which you can characterize as a gully erosion. This is the 5.8 meter spatial resolution satellite data. Even you see in the forest area, this is the forest, and you can see those linear features you can characterize as a gully. So this is the same picture but more zoomed, and you can say that linearly this one is the gully is coming like that one and moving, and it is coming into this stream. So now satellite data can be interpreted, but this lecture is devoted to how we can estimate soil erosion rates using GIS and especially distribution erosion rates. So that is the main focus of this lecture. So I will go through that. But before that, we should know that is what are the factors for soil erosion, because those factors we need to calculate. Then only we can go for the quantitative assessment of soil erosion. One is the soil erosion is major factor is rainfall, where you are getting two things: rainfall intensity or rainfall erosivity, what is the power of rainfall; runoff, how much runoff water is generated; then soil. Then soil we characterize that is this soil is erodible or not. So how erodibility of soil is there, we calculate the soil erodibility. Topography is another factor, means you know the steep slope and gentle slope, means slope is the one of the important parameter for the governing the erosion. So length of the slope and gradient of the slope, two parameters are important. Then vegetation cover, it is covered under the forest or agriculture or which type of vegetation. Sometimes vegetation also degraded vegetations or dense forest, dense vegetation. So vegetation conditions we need to quantify that one. And then what conservation measures are being taken at present. Sometimes farmers do various conservation measures to protect their land, protect their soils, and even the forest area also there are various conservation measures are taken. So that we should know that is what conservation measures are there, measures are there or not there. So you can say these 5 factors affect the soil erosion. So I will go the first factor, that is climate factors. Climate factors mainly here I am calling it is rainfall factor, and we calculate the rainfall erosivity. How rainfall erosive? Because when rains are coming, it having a lot of energy. If rainfall having high intensity, what do you mean by intensity? Means rainfall in how many rainfall in millimeter per hour. So rainfall per hour is rainfall intensity. So in general, sometimes drizzling is there, it means rainfall intensity is low. If sometimes very heavily raining, the intensity is very high. If it is heavily raining, rain intensity is high, then it has lot of energy, and then it has more power to detach the soil particles. So erosive rains, it has been classified that in India we consider if rain is less than or equal to 10 millimeter per hour, then it is not erosive. So we take when rains are more than 10 mm per hour, in 1 hour more than 10 mm rains are taking place, then only we call it is erosive rains. And some countries consider this limit as a 25 millimeter per hour. So, and this rainfall intensity, indirectly it represent what is the size of the particle, what is the mass of the rainfall particles, and what is the velocity of rain. So, because of velocity, you know, it is you can convert into the kinetic energy. So, for the rain, we calculate the energy, that is rainfall erosivity. And rainfall erosivity, mathematically, it can be computed as a summation of kinetic energy K and EI, erosion intensity of 30 minutes. 30 minutes, in 30 minutes, how much erosive, what was the intensity of the rainfall, that was taken into account. And kinetic energy K can be calculated by this equation, that is 11.87 plus 8.73 log 10 I. I is the intensity of the rainfall. So, using these equations, we can calculate daily rainfall energy, then daily to monthly, monthly to annual. So, in general, erosion models takes into account the total kinetic energy in a season of the rainfall, rainy season, or sometimes it is taken as a annual, means entire year, what was the kinetic what was the rainfall erosivity in this region. Second factor is soil erodibility factors, means how your soil is susceptible for erosion. So, erodibility factor K, how I can estimate mathematically, I want to know the some value, because we are going to use in the erosion model. So, K value need to be estimated. We can estimate K value for our soil map units. And you know, for the you can collect the surface soil sample and calculate the K value using this formula, where it requires M parameter, which is related to the particle size parameter, means how much sand, silt, clay is there, silt plus very fine sand and clay particles. If you know this one, then you can get the M value. A is the organic matter, B is the soil structure code because soil, if well developed structure is there, then we give value 1. If structure is poor, then we go to the maximum of 4. So, we can characterize, that is what soil structure is there, and on the basis of that we can give this value. Then C is the profile permeability class, means if a soil is permeable to infiltrate the water, rainfall water. So, if its permeability is very fast, rapid, then give 1. Otherwise, if soil is very hard and clay soil is there, water are not able to move inside, then we give very slow permeability and define as a 6. So, if you know this very simple parameter, mainly texture and organic matter, if you know, then you can calculate this K value, soil erodibility. And third factor is your topographic factor. Topographic factor or rain factor, terrain factor. You can see there is 2 factors are there. What is slope length? This is I shown the individual field, what is the length is there. So, individual length we call it is slope length, because water is moving from here to here. So, some water is moving like this one, then field length can be known as a slope length, and we need to calculate the slope length factor. Another is the slope. What is the slope is there? Means steepness of the terrain. So, you see that is the steepness. So, if you know the slope degree map you have generated yesterday, which I discussed, then you can get, from that you can derive the slope steepness factor. And combinedly this L and S, we call it is topographic factor, LS factor. You see here a beautiful landscape of terraced agriculture field, and this is the hills, and you see that is the, what is the slope. Here the slope is high, here the slope is less. So, slope length is steepness factor, because if you have derived the slope map you can generate. But slope length, length of means field length. what is the width of the field, calculating for all the area for watershed, it is a very difficult task. You cannot do for entire all the fields, you cannot measure, but we need to measure for to define length. So in GIS we have there is a functionality has been developed, so that flow accumulation map, which I will talk today also, and with flow accumulation map you can generate field length map, or we can say the slope length. So this problem we can solve using GIS. So in GIS, L and S factor both can be generated very easily, which is very tedious if you go for the measuring each field. So for slope length, in the recent erosion models, which is written here, the Rusley model. So I will come what do you mean by Rusley, but the recent instead of field length, we have replaced this word with the flow length, or you can say the overland flow path length. So that field length definition was replaced recently. Now we are considering in GIS for the sake of GIS or for use in GIS. In that, what do you mean by slope length? That is the particle where from it is detached and where it get deposited. The length between this area eroded to deposition is known as a slope length, and this slope length can it also can be termed as a flow length. And if you generate the flow accumulation map, then we can generate the slope length map of the watershed, and that is the real solution we can get for avoiding the measuring single field length. Fourth factor for soil erosion is your vegetation cover. You know, the vegetation provides the protection to the soil against the rainfall, because rainfall having the erosive energy, and if it is fallow land, there is no vegetation, then it will hit to the ground directly, and therefore your soil particles will get detached. But if it is protection is there of vegetation, then it will hit through the plant leaves and tree leaves in the forest, so that its energy is get dissipated, reduced, and because of that it will not directly able to hit the soil particles, so it will not detach. So vegetation cover provides the protection to the soil. And another advantage is that if rain its energy get dissipated, then it will move to the surface. Then because of stems and because of roots, the flow of the runoff water will also reduced. So it also helps into reducing the runoff velocity, and it improves increase the infiltration. So more will be the infiltration of the water, rainfall water, then less will be the runoff generation. If runoff generation is less, then you can say that is the less energy will be able to move the soil particles from the surface. You see how it works. That is your vegetation. Suppose plant leaves, raindrops are intercepted by vegetation or leaves, and then less energy is rainfall falling over that, it has less energy and it will reduce it will not able to detach that soil particles. Another is that is this material is adding the organic matter to the soil, and because of organic matter the structure of the soil will improve, and as the structure is improved, then more infiltration will be there, and if structure is well, then you know the soil erodibility will be decreased. So it has manifold advantage to the plants. That's why farmers put sometimes mulches in the field. Sometimes in the rainy seasons, if you go in the hills, farmers always try that just before as soon as possible during the monsoon period, the soils should remain under the vegetation cover, so that erosion will be less. Another farmers what do, that is the management. He do the management, and its major purpose of management is that provide surface protection from the rain. So that's why he uses mulching. So vegetative mulching or stubbles of the previous season crop he spread over on the field. Also farmers do some mixed cropping, or some he do the strip cropping, and he do the contour farming. So one slope he put one crop, and another slope he put another crop, like that one he do. Terraces, he develops the terraces, as you are seeing in the field, hilly area, the terrace fields. Sometimes for diversion, water, run of water, he safely keep aside, that is the diversion should be there, so that velocities, run of water should go in a without damaging the agriculture field. Impoundment means collection of the run of water in the tank, or sometimes he make the ditches or trenches in the ground, in the field area, so that water get accumulated there, so large amount of run of water doesn't flow. So you see the cover, what he do, that is, this is the, suppose the in the, he put, that is the in a line, that is a strip farming, he putting the mulches on the surface, he has put the previous seasons the crop residue, so that it provides the protection to the surface. So in this this be support practices. First is, that is cover, we call it is C factor, and management we call it is P factor. P factor. So you can see that is the P factors value. All the C factor and P factors value ranges from 0 to 1. So depends what, if he is not doing any management, you can say the P value will be 1 if no management. If there is no crop cover, area remains fallow, C factors can be 1. But if suppose he is putting some, there is some crop, then C value will be less than 1. And P value, if he is doing strip cropping, contouring, or terracing, any management practice, then P value will be given to less than 1. And how we will give this value, you can take from the reference literature book. Those things have been already established by the research organizations, and that you can take the direct value. But only you have to map those vegetation cover or land use land cover map using remote sensing data. So this was the soil erosion factors, and how those factors is affecting soil erosions, we have discussed that one. So I can say in summarize, that is the rainfall, soil erodibility, topography, land use land cover, under that vegetation cover, and management practices. These factors are responsible for soil erosion, and if we know the value of that one, then we can calculate the soil erosion rate. So now I will go for the erosion models. How these erosion models helps to quantify the soil erosion rates, and how we can implement remote sensing and GIS. Why we need model? First of thing, we need model to estimate important quantities, means erosion rate. How much erosion rate is taking place? We want to know, because rate of the erosion, if we know, then accordingly we will go for which kind of soil conservation measures we need to take. To meet the design requirement, for design for soil conservation measures design, for example, suppose if you estimate the runoff amount, how much runoff will be there, then based on the runoff, you can go for that which kind of mechanical structure I have to design, or what kind of that is trenches has to be developed in the field. So for many designing purpose, you need the quantitative estimation. Model is important if you want to predict the future erosion rate, future requirement. So for future we need model, and it helps overall guidance. It provides the guidance for them taking the management action for soil and water conservation. But models always it is not so easy. You need to have some experience, or you need to go very carefully. Actually, most of the models, all the models has been developed for the point based, for a point, for a particular experimental site, experimental field, research form, where the researcher has developed the models to estimate the soil erosion rate. So you can say the field level erosion assessment models are there, plot level erosion assessment models are there. But in GIS and remote sensing, we are going for the spatial assessment of soil erosion, where this field plot is the point model, point based model, so they ignore the spatial variability. So one of the problem where we are going to make the large area estimations, though, so therefore we will lose many of its because of spatial. We are doing averaging one, so many times it overestimates or underestimate your soil erosion rates or runoff rates. So that is the problem with modeling. Models are often difficult to build. It is not very easy to develop the models, because you need to do the continuous experimentations for years, collect the data, and then you make the relationship of one factor to another factor, and then you can use the develop the model. So model is difficult to build, use and understand. So you have to get understanding of that one. There are few common general models. Their models are there and has been customized in the GIS softwares, or that has been customized by the open source softwares. So they are available, so we are using that one. Models response is often wrong, because you have to models have been developed for one area. For example, suppose it is developed in the US, Britain, and we are using in India. So how the climatic situations, geological situations, all farming practices are different there, and we are using here. So we have to calibrate the models. We have to calibration, validation, then we can extrapolate for large area. If unless you are not calibrating, then response of the models is in general will be wrong. So it is not so easy. You have to first understand the model, which parameters it requires. So very carefully you have to define the parameters. So we are going to discuss how we can do the erosion models. So models is you can say is the process of mathematically describing soil particle detachment, transport, deposition of land surface. So modeling is mathematical description of your erosion processes. So each process, how it detach, what energy it will require to detach the soil particles, how it will transport, where it will deposit. If mathematically kinetic you solve the equations, those equations, then you can calculate the soil erosion. So solving those equations are not so easy. This is given one classical example. You can see when there is a hill slope is there. So you see here it is shown the sediment load, and here it is shown the transport capacity. So your runoff water in beginning have the high transport capacity, so it detaches the more amount of the sediment. But as we move, then your transport capacity, when it is higher than your sediment load, then erosion will take place. But once your transport capacity becomes lower and sediment load become higher, then from this point the deposition will take place. So erosion when transport capacity is high, and deposition when sediment load becomes higher, then deposition will take place. This is on the hill slope, we can see that one. So for erosion modeling, the first the beginning was done by one renowned scientist, Wismir and Smith. They have done experimentation in 1960s in the entire US, different type of soils, different type of vegetation, different types of topography, he prepared the plot. We call it is erosion plot, and later on it is called unit plot. And he given the plot size 22.1 meter length, 1.83 meter wide, and 9% slope he maintained. And then this measurement, he calculated the soil erosion rate by collecting the sediment in the tank at the end of the field, collected the total soil loss in the tank, and he measured, that is, in this unit plot, how much soil is getting lost. So he did the experiments, and in the entire US, and in 60s and in 70s, he for the public, he developed the first erosion model by Bismuth and Smith in 1978, which is being used most widely in the world. So erosion models, we can say, we can divide three. Today various erosion models are available. Some models are very descriptive, and where all the process are being taken care. So you can divide in three empirical models, that is the primarily based on the observation and usually statistical in nature. These models are based on the statistical relationship. They are also known as a black box model, where we don't know what processes are taking place. We know only if what is relation of rainfall and soil erosion, what is relation of vegetation density and erosion rates. So it is the statistical relationship has been developed based on the observation by conducting the experimental plot, as I showed you in previous slide. And the first model was developed is USLE, Universal Soil Loss Equation. Then over the period from the 1978 to today's, lot of science has been developed, and erosion science has been developed, and those groups is still today working. USLE, Bismuth, Smith, those who started the experimentation, and they developed the process-based models also. And today another kind of model is there, where totally we know the process of detachment, transportation, deposition, all the equations, all the process has been solved through mathematically, and the complex interaction has also been solved, and this is the known as a physical based model. And this physical based model we know as a white box model, means where all the processes are cleared, we know what process are taking. So physical based models are very exhaustive, very descriptive, where all the erosion process are described. So physical based models estimate soil erosion on daily basis, weekly basis, monthly basis, and annual basis. But empirical models, they are assess the soil erosion on the seasonal or annual soil erosion rates. Annual, not daily, not weekly. And another group of model is the semi-empirical models, and semi-empirical models are in between of empirical and physical based, where some of the process are more described in semi-empirical models. So you can say the beginning was this, and today we are at this position, and in between that various years these models has been developed. What are those models? We can see the some list I have given here. Empirical models is USLE, which is plot model or hill slope model. RUSLE, revised universal soil loss equation. This is universal soil loss equation. It is also calculated, you see the annual loss. Physical based model, the most common model is WEP, Water Erosion Prediction Project. This is available on the hill slope model and watershed model. It gives the continuous soil erosion estimate. And as you know, there is a descriptive models, physical based process model. So all the physical based models are computer models, computer simulation models. So they need computer, the program. So all the equations has been written in algorithm softwares, and they run on the your window based softwares today are available, so you can run those models in that, and all these physical based models you can download from the internet freely, and you can use that one. They have the experimental data also they have shared, so that you can run models and you can learn. Another model in between, that is the conceptual model, where the more descriptions are given but less than this physical based. Among that example is Apex, SWOT, AGNPS. So one example of all the models I will give my presentation. We go for the empirical model. Empirical model, which is, I told you, that is the, in the very beginning in 1965 it was developed by Wismir and Smith. Later on it was released for the public in 1978. They have conducted 10,000 plots experiment throughout the USA, and this is the simple equations they have given. A, annual soil loss, RK, LS, CP. What is the R? R is the kinetic energy, EI30, which I told you earlier. K is the soil erodibility. L is the slope length, field length. So any length is there of your field. Suppose your field is L, length is there, divide by 22.1 to the power 0.5, you can get L value. And this is the slope, steepness. So slope map, theta is the slope degree in radians. So sin theta, these equations, and C and P you can get from your land use land cover. C is vegetation cover, P is the management practice. So you see that one, more details of that which I described to you just. Another models which is most commonly being used in the entire world, and today all the erosion study mainly they are using Russell model, revised universal soil loss equation. This model is very well integrated with your GIS. So all GIS community, geospatial community is using revised universal soil loss equations. This is the advanced form of your Russell model, and it was developed in 1997 by Renaud et al. Actually, the Russell model was developed for the agriculture area, but later on in a watershed you have the also the non-agriculture area, forest area. So Russell models cannot be used there. So Russell models can be utilized here, and this model the structure was remain same as RK, LS, CP, but only the sum of the factors calculation methodology has been revised. Here EI30, rainfall erodibility remains same, but earlier it was annual or event, but now it is seasonal based erosion, rainfall erodibility you can calculate. The major improvement was that here he has given that if slope is less than 9% and slope is more than 9%, then two different equations are there. But in Russell model, only one equation was there for S factor, any slope. Okay? And another is that in Russell, they have defined the field length as a flow length, which I told you earlier, that is they replace with the flow length, so that flow length we can calculate using digital elevation model. So every field length calculation is not required. In GIS functionality we can see here the slope length. You see this is the DM. You can generate the flow accumulation map, and you know that each pixel is showing, the number is showing that this pixel is receiving runoff water from how many pixels. So suppose it is receiving from 2 pixels, and this 2 pixel you can multiply with the size of the pixel. Then suppose size of the pixel is 20 meter, then 2 into 20 become 40. Then 40 become your slope length, flow length, and flow length factor. If you divide by 22.13, then you can calculate the L factor. So L factor can be very easily calculated. So how we are doing that is we create the flow direction map from DEM, calculate the flow accumulation map from DEM, and by using these two maps we get flow accumulation map. And this flow accumulation map, where you are getting the digital number, that you can multiply with the size of the pixel size, and then you can get that is the divide by 22.13, which is the plot what Bismuth and Smith has defined the plot size 21.13. That plot size was divided by that one, and you can calculate the flow length. So flow length calculations becomes very easy in this equation. So this was the real breakthrough for GIS modeling. And S is also changed, improved for the two solar factors, and C and P remain same as earlier in the Usle models, but even C calculations they have improved. They have said that is the in beginning the vegetation cover is very less, but at the crop season advances the length is there. So monthly C factors when we can use in this one. So one problem used to come in the rainfall erosivity factor, which I told you that you can get from if you have daily rainfall data from automatic weather station or weather data. But many times this data is not available. Daily rainfall data is not available. You are having monthly or annual data. So for that one, some scientists have Singh et al. In 1981, or they have established some formula also, that from you can get from the annual rainfall erosivity you can calculate using this equation, where X is the rainfall in a season or rainfall in a year. So you just annual rainfall you are having, then as a X you can replace that one and you can calculate Y rainfall erosivity. K map soil erodibility factor. Sometimes it is ready-made value is also given based on the texture. Suppose you have the texture information about your soil in your soil map. So based on the texture it is known that is the K factors. The highest K factors you will get, which soils are most different textures will having different K factors. Soils with the silty textures will have high erodibility. You see, silty soils is going 0.6 even. But clay soils are having less erodibility of the soils, this one 0.13 to 0.26. If clay content, silt content is increasing, then your soil erodibility is increasing. So from the soil texture, if you have soil map, you can calculate, as I previously told, that is K factor map, K factor can be calculated with the surface sample data, soil surface samples. Otherwise, sometimes with the organic matter and texture, then we can assign with literature also. So I have described already this LS factor calculations, which is one of the most important part. Then you have the land use, then the problems comes, that is the remaining two factor, C factor and P factor. These C factors we can give based on the land use land cover map. You can prepare from the remote sensing data land use land cover map, as I told you earlier previous lecture, that is a satellite data can be used for mapping forest cover, fallow land, crop land, scrub lands, different land use land cover map can be prepared. And based on the literature, you can literature and reference, already scientists have defined that is what C factor should be there. So you see that from there you can define the C factor. You see for the dense forest, C factor is 0.001. But factor for paddy crop 0.25, for maize crop 0.37. So C factor and P factor are less than 1, and you can give as per your land use land cover. P factor is the management. Paddy fields are having the terrace agriculture, we have defined 0.3. Maize also terraced, but maize is cover is less. Its terraces are not so well developed, but here terraces were very good. That's why we have given 0.3, here 0.5. So C and P factors, you get CP factor. So you can, here you can see that is climate data, soil map, topographic data from DEM, land use land cover map you can get from remote sensing data. So C factor and P factor you can define and integrate in this one, you are getting soil erosion map. So I am showing you one example that you see, that is the one watershed in the Dehradun region. This is the forest and this is the cropland, whitish you are seeing. In this area we prepared the soil map, and soil map used to derive the soil erodibility map, K factor map. We have taken the digital elevation model. Using these equations we have developed the LS factor map. We have taken the land use land cover map generated by visual interpretation, or you can generate by digital classification, different type of land use. This green is forest, these are the scrub land, red is a scrub land, yellow is agricultural land, and we can define the C and P factor value in GIS. Then you can integrate all those things and you can get the soil erosion rate for every pixel. Every pixels you will get soil erosion value, and these soil erosion values you can classify. If less than 5 tons, then very low. 5 to 10 tons per hectare per year, then it is low. If 10 to 25, then it is moderate. Like that you can classify soil erosion classes. So you can prepare very low, low, moderate, high, severe, very severe soil erosion rates in your area. So you see this is the very low soil erosion rates, but red is showing very severe soil erosion rate. Very severe means you can say more than 75 tons per hectare per year. Process based models, which I told you, this is the computer based model, continuous simulations. This is the new generation models developed by US Department of Agriculture in 1995. It was developed with the pace as the computer science has been developed. And this process based models takes soil erosion, infiltration theory, hydrology, soil physics, plant science, hydraulics, and erosion mechanics. All process it takes into account, and then it calculates. So it is a very descriptive models, white box models, where all the process has been mathematically described, and algorithm is written in the computer software and you can run. So this is the screen of the WEP model, water erosion prediction project model. A screen will appears like this one, where you can define, you can calculate daily, monthly or annual. All type of soil erosions you can calculate in this WEP model. WEP model is the most advanced models and today being used for, actually this WEP model you cannot use for the large area. This is the model has been developed for the research tool, experimental tool, where you want to know about, understand the various processes of runoff and erosion. So that's why it is used in that case. It's a GIS, WEP model was, earlier it was not GIS version, later on WEP was integrated with GIS and it was named as a GeoWEP model. So you can say the ArcView software or ArcGIS software, it is integrated now and available for as a GeoWEP, and these models are for, can be used for as a experimentations where we are using watershed less than 500 hectares. So process based models, as it requires lot of information of soil, vegetation, every weekly vegetation informations, growth, plant density and other parameters, climatic daily rainfall data, even hourly rain, every 15 minutes rain data is required. So these models cannot be used for large area. Process based models in general used for the small area for as an experiment and research tool. For studying this one, Indian Institute of Remote Sensing developed the watershed observatory to test all these models. So this is the automatic weather stations we have established in a one small watershed was 58 hectares land, and we keep here, suppose the runoff water is coming, then how much water is coming, how much sediments is coming, how much nutrients is getting lost. We are analyzing all these things at watershed, where we are having surface runoff gauge stations, portable suspended solid analyzer, automatic weather stations, sediment sampler. Many instrumentations has been developed here, and we are measuring. So we are measuring daily what is the sediment loss. Suppose that is the per rain we are getting loss of 68 kilogram per hectare, and nutrient nitrogen loss is getting 1.29 kilogram per hectare. So this type of measurements for watershed we have developed. Here, this was the small watershed where I was talking. We have developed the site at this place. This is the forest area. This is the crop land. So we have a cartoset data where you are having the more detailed information. So you see the soil map and land use map was generated, and then we tested the various model. We tested the Rusle model, we tested the Apex model, process-based model, WEP model, SWOT model in this watershed, and we calibrated, because for calibration purpose you need the measurement data. Then only you can use the process-based model. Process-based models cannot be used without calibration. Although empirical models and semi-empirical models you can use without calibration as well. Suppose Rusle model, that's why they are most widely used and large area it is used. But Apex model or process-based models, they need to be for a small watershed where experimentations or measurements you want to quantify. So this is the Rusle models we did for that our watershed. So we generated the various layers as I described, and we calculated the average soil loss. So maize crops are, we find that is average soil loss is 24 tons per hectare, but paddy crop area is getting 14 tons per hectare. And maize and tree, where maize and tree agroforestry was there we are getting 15.87 average soil loss. So in the forest we are getting 9.65 tons per hectare per year. So we are able to quantify the average soil erosion rates in various land use, land cover. So this information is important for your conservation planning. Here you can see one thing is that we need to estimate the surface runoff also. How we can estimate the surface runoff? There is a one formula, empirical, all the erosion models use this equation given by USDA as a SCS curve number method. And SCS curve number method here, R is the rainfall and minus 0.2 S. S is the retention parameter. And S we can calculate by this equation, where divide by Cn, and Cn is the curve number method, and curve number depends on the your land use, soil and topography, slope. So on the basis of Cn we can find out how much watershed itself will retain the water. So what the rainfall is falling, that rainfall, how much it will be absorbed by the soil and it will be retained in the depression, that is taken care by S factor. So our rainfall minus 0.2 S and to the power square, and this by these equations we can calculate the how much runoff will be generated. So we use the for runoff and soil erosion estimation, one model are used, SWOT model, soil and water assessment tool, which calculate on the daily time step and monthly, or you can calculate runoff, erosion, sediment loss, even nutrient transport, and these models can be downloaded from the website. Okay. So we use the SWOT model, and we find that it in my watershed, that is the red area is showing the high amount of, blue area is showing the high amount of runoff water, red is the followed by this one, and this area is showing that is the less runoff area. You see here, less runoff. So where is the runoff is more, where is the runoff is less, that information is very important for your soil and water conservation planning. So you can do with the SWOT models. Another models we tested the Apex model. This models is used for the estimating the soil nutrient loss, nitrogen, phosphorus, potassium, how much loss, erosion rates and runoff rates. So we can calculate the erosion rates of the watershed, and that is, it is showing that is here we are getting high erosion rates, but here the erosion rates is less. We use the WEP model, water erosion production project, which is the most advanced model. And this model beauty was that you can find out the erosion at every place. Suppose this runoff water is falling, and then which in the upslope area, mid slope area, or in the lower slope, what is the erosion rate at different field. So we calculated the erosion rate like this one, 12 ton top of the hill. But here you are saying that is 21 and 19 tons per hectare per year. It is written 2.1 or 1.9, but if you convert in tons per hectare, it will come 21 and 19 multiplied by 10. But we find that this slope area is having the highest erosion rate, 3.6, but average erosion rate is 22. So if you do with Roussel, then you will get the average erosion. But web model provides you erosion at at a regular intervals you can estimate. So purpose was that which place we are getting highest erosion. So we have used the web model, tested the models, and then we find that is yes, this is, we found that is landslip is occurring, or collapse of the terraces are occurring at this slope, not at this slope, because you see the rain erosion rates is very high, 3.6, 36 tons per hectare. So different slope positions in the hills witness different erosion rates, not one erosion rates. But where is what erosion rates, if you want to understand, then you have to go for the process based model. So you can see that is the process based models are available for a detailed study to understand the processes, to understand the its erosion process and understanding the runoff generation process. If you want to understand more, then I, out of this experimentation in my watershed observatory of IIRS, I published some of the papers which are very, you can study those papers to go for details. Suppose this is paper published recently in this year, modeling daily surface runoff, sediment and nutrient loss at watershed scale using apex model. This is published currently in Environmental Earth Science International Journal. Another paper is that I published this in modeling runoff and sediment yield using GeoBAP web model, where you can see that is published in International Journals Modeling Earth System and Environment. We use the Roussel models for simulating climate change impact. So in future coming 100 years, what will be the impact of climate on soil erosion? That was studied in the mid Himalayan landscape and using Roussel models. So this paper you can read for your Roussel erosion modeling for climate change prediction, climate change impact prediction. This model was a SWOT model to simulate, that is where the runoff will be generated, what will be its variation, spatially distributed surface runoff generation. And this model, this paper was give you idea about the how to prepare the soil erodibility map, because soil erodibility, I told, that is very difficult preparing for an area in watershed. So with the surface samples, how we can generate. And this paper is very widely used referred by the various researchers, that was the modeling soil erosion using Roussel 3D model. So these are the few papers which you can read and you can get better insight. And if you have any in that any questions or you find some problems, you can always email to me. I will reply over that. Thank you very much. Now I welcome you all for question after 2 minutes. Yeah. Yes, the question how to use watershed management in environment conservation like tree protection. Actually, watershed management includes any practices you are doing for soil and water conservation. If you are doing soil and water conservation means you are also working for the protection of your vegetative vegetation like perennial vegetations, or you are working for agriculture field protection. So tree protection nothing but you can say if you are keeping the forest cover, or you are doing the afforestation, it will help for conserving soil and water, so it is part of watershed management. How GIS shows the soil erosion of slope? GIS is a software, is a tool which integrate various maps, which integrates various maps, so that you can analyze those. By integration you can analyze those for another, you can do the spatial analysis. So I told you the soil erosion depends on the various factors, that is your soil, vegetation, topography, land use, land cover. So those maps can be generated in through using remote sensing data, and can be integrated in GIS to assess the soil erosion, and topography is one of the parameter. How to form gully? Gully is the advanced form of minor depressions. I told you that first rills forms, and rill is the, if you I show you the depth of the rills and size of the wideness of the rills. So these are the small channels. Small channels, when it is less deeper and less wider, then we call it is rill. And when it becomes very large and deeper because of erosion, then these no, these channels are known as a gully. How much erosion affect the coarse soil particles in plain area? Coarser the soil, will water will infiltrate into the soils, so you will expect because of that soils are not more erodible. So in the plain area, erosion coarser soils will absorb more rain water, so runoff will be less, so erosion will also be less. Then if we, but the topography, if sloping area is there, there we get more erosion. Can we calculate sediment yield from watershed without observing sediment data using SWOT models? SWOT models, you can predict the sediment yield, because in sediment yield it uses modified universal soil loss equation. Modified universal soil loss equation, that is MUSLE. This model is similar to the RUSLE model. Only the difference is that instead of rainfall energy, here we use runoff water, surface runoff water. So surface runoff is replaced with the rainfall energy. So SWOT models calculate the sediment yield, predict the sediment yield. Observed data be required for calibration of the SWOT model. If you have no observation, then we cannot calibrate the model. If you are not calibrating the model, then your all the predictions will be, or computation of soil sediment will be wrong. So that's why always these models, process based model or runoff models or sediment models, are need to be calibrated, and then you need a observed data. How mathematically describe about modeling? In modeling, you are computing the value. erosion rate, quantity. And quantity you can, unless you are parameterize each parameter in terms of number, then you cannot go for modeling or you cannot go for mathematical computation. That's why modeling means mathematical computation of your output based on the input you define digitally, digital numbers. How to determine the erosion methods that can be used for any specific area? There are various erosion models are there. Some model, then you have to see that is how much parameters, each models requires various parameters or input parameters. What parameters you are having, or you can derive that one depending on your resources for the area. Suppose process based models requires climate data or weather data in very detail. In every 30 minutes rainfall data you require, rainfall intensity data, you require wind erosion, wind direction, solar radiation, flow, and other parameters, temperature parameters. If those things are not there, then you cannot use process based model. Empirical models, which is when you are having less amount of data and the data are not very exhaustive or very weekly or monthly data are not there, then you cannot use process based model. Can we use Usle, Rusle, Musle or terrace for terrace farming sites? Yes, you can use Usle, Rusle, Musle, all models in the terraced agriculture lands, and I have shown in your my publication that those all the models has been tested in the terraced agriculture lands. So that is the some for topographic terrain derivations you need to take care of, but you can use these models. Watershed management question is there from Abhinav Yadav. Watershed management means storing of water and maintaining of water bodies in a field in a dig hole. No, watershed management doesn't mean that. Watershed management is managing your resources of soil resource, water resource, geology, vegetation, all resources in a very sustaining way, and that you do all those measures to conserve the soil from erosion and to restore the water, what is from the rainfall, what is the runoff water is there, that runoff water should be stored in the watershed itself. So watershed management is a holistic approach where you are adopting various soil and water conservation techniques as well as enhancing the agriculture crop yield production, as well as you are improving the livestock, you are providing the pasture lands or grassland for livestock development. So there are various components are there, and major aim is that you protect your land from degradation in future, you conserve your soil, so conserve your water, because water get lost from your area, so the water should be used to recharge your soil or recharge your groundwater, so that you can get more and more vegetative growth or more and more crop production, not only the storing the water. What is the LS factor and how it correlates with the CP factor? LS factor you are calculating the based on the slope length and steepness of the slope. It is the topographic factor. So from DM you can calculate LS factor, but CP factor you calculate from the land use land cover map. So CP factor both are different parameters. One is the vegetation, one is the topographic parameter. How they are correlating? You can say you can study it vary in the area to area. Sometimes if LS factor is very high, there may be less vegetation, and if LS factor is very low, there may be very good low LS factor area in general for the cropland area. In agriculture area are practiced on the lower slope, but higher slope area it is higher slope area means high LS factor. There you will there in watershed generally the forest cover. So forest cover are lying on the high LS factor area. So you can, but you can analyze in your watershed, that is how it's having the relationship. What is the criteria for assigning P factor? P factor value and C factor value, you can, for P factor first you see that is what conservation measures farmers are adopting in their area. Suppose he is doing strip cropping, he is doing bunding, contouring. So keeping into account that, then you assign the P factor. So P factor can be assigned based on the literature, or some references are available for soil erosion manuals. From there you can assign the P factor value. So Rajasthan soils has the lowest erodibility. If you see, that is the sandy soils in Rajasthan, they have low erodibility. But Rajasthan, if you see the Aravalli, and you see that where the Kota area, their soils are heavy textures. So their erosion rates will be high. So soil erodibility is one factor, but erosion rate depends on the 5 factors. So one factors you can see how soil is affecting the erosion, so that is depicted by soil erodibility. Other than ArcView, what other softwares can be used? Web model. Web model is available with ArcGIS. ArcGIS interface are available, and you can download that one and you can use with ArcGIS software. Is soil erosion one of the reason for landslide? Soil erosion is not the major cause of the landslide. Landslides means collapsing of the land. So it is mainly the slope failure and oversaturation. It is basically the slope failure. So soil erosion, it is not, you can directly you can say that is related with the landslide. Why we always make triangular boundaries of watershed? Does watershed management only include the calculation of soil erosion? I have told here this lecture was denoted describing only geospatial method to estimate soil erosion. But watershed management, soil erosion estimation is one part, where we require to compute the soil erosion rates to plan soil and water conservation measures, and that measures is suggested to the farmers and implemented at watershed development committees are there, where farmers are part of those committees. So they operate or they do their conservation measures based on the suggestions. ARC, Apex and GeoBAP open source or does it come at ArcGIS extension? No, BEP, GeoBEP is a open source software, and ArcApex is also Apex is software open source. GeoBEP is open source software. Only ArcApex, this Apex software can be as an extension of ArcGIS. You can add that one, add on, but the independent softwares are available, which need ArcGIS to interface that one. So if you are having ArcGIS, then you can interface the Apex and GeoBEP model. They are freely available and you can download from the website. Clarify the rill and gully erosion. Rills are Gullies are advanced form of rill. Rills are depths are less, you can say less than 70 centimeter, but gullies are more than 70 centimeter deep, and width of rills are also less, 20 to 70 centimeter wide, but gullies are more than 1 meter wide. So gully is advanced form of the rill. Does watershed management interact with farmers to improve the crop productions? Yes, watershed management programs are implemented on the ground, and we see, the soil and water conservation officers are there in every district. They implement the watershed management program. They develop for one watershed and implement that one, and then they see. We will see in the last lecture how watershed management program is being implemented at ground level, and how we are using GIS remote sensing for monitoring of the watershed. So the on the 6th August last lectures, I have invited a renowned guest faculty who is working on monitoring, who has developed the tool for monitoring of the watershed and how it is being implemented on the ground. So you can listen on that day, last day, and then you will get the clarity over that. Can we predict the possibility of mangrove afforestation? I am not talking about the afforestation. Can we use Rusle model to the wastewater treatment plant in sediment process? No. Rusle model used to estimate the sediment in the agricultural land, forest land, and in urban area. How to create dam for a smaller area like 5 to 10 hectares? 5 to 10 hectares are very small size. There you can create the dam by DGPS survey, or you can do by the using UAV drone. So there you can get for a small area digital elevation models up to 25 centimeter or 100 centimeter you can generate. There is any solution to stop erosion? Yes. Tomorrow I will discuss these suggestions in a very detail. So I will tell you how to conserve the soil erosion. There is a soil erosion models for coastal regions. Coastal regions or plain regions or hill regions. Erosion models are same. You can use Rusle models for soil erosion estimation in coastal area. Can we use watershed management in desert area? Yes, you can use watershed management in desert area. You can compute, that is runoff, how much runoff will be there, because in runoff and soil loss you can calculate. So desert area mainly water conservation is, rain water harvesting is the problem, and is major issue, and that you can using that digital terrain analysis you can go can characterize, that is which part we will requires to conserve the water or rainwater harvesting structure. Gully erosion cannot be controlled by tillage operation. Gully erosion you can do by various measures which I will discuss tomorrow. Can these models estimate or calculate the soil moisture content? No, these models are not used for soil moisture estimation. Can we identify ideal location for water recharge site? Yes, you can identify the suitable sites for water recharge or rainwater harvesting using terrain analysis, using your SWOT, SWOT models, which tell that is how runoff will be generated in your area. So this runoff generation, especially distribution runoff generations, will help you to identify the site for recharge recharge site development. Any erosion models, especially for India? These erosion models in India also, Rusle models and Rusle model are widely being used. You can use that one. Okay, thank you very much for joining this session, and I will meet you again tomorrow 4 o'clock to discuss with soil and water conservation planning, or you can say what are the soil conservation measures we are adopting for watershed management. Thank you.